addressing modes are an aspect of the instruction set architecture in most central processing unit designs. The various addressing modes that are defined in a given instruction set architecture define how machine language instructions in that architecture identify the operand, S, of each instruction. An addressing mode specifies how to calculate the effective memory address of an operand by using information held in registers and/or constants contained within a machine instruction or elsewhere. In computer programming, addressing modes are primarily of interest to compiler writers and to those who write code directly in assembly language. Caveats: note that there is no generally accepted way of naming the various addressing modes. In particular, different authors and computer manufacturers may give different names to the same addressing mode, or the same names to different addressing modes. Furthermore, an addressing mode which, in one given architecture, is treated as a single addressing mode may represent functionality that, in another architecture, is covered by two or more addressing modes. For example, some complex instruction set computer architectures, such as the Digital Equipment Corporation VAX, treat registers and literal or immediate constants as just another addressing mode. Others, such as the IBM System/360 and its successors, and most reduced instruction set computer designs, encode this information within the instruction. Thus, the latter machines have three distinct instruction codes for copying one register to another, copying a literal constant into a register, and copying the contents of a memory location into a register, while the VAX has only a single MOV instruction. The term addressing mode is itself subject to different interpretations, either memory address calculation mode, or operand accessing mode. Under the first interpretation, instructions that do not read from memory or write to memory are considered not to have an addressing mode. The second interpretation allows for machines such as VAX which use operand mode bits to allow for a register or for a literal operand. Only the first interpretation applies to instructions such as load effective address. The addressing modes listed below are divided into code addressing and data addressing. Most computer architectures maintain this distinction, but there are, or have been, some architectures which allow all addressing modes to be used in any context. The instructions shown below are purely representative in order to illustrate the addressing modes, and do not necessarily reflect the mnemonics used by any particular computer. Number of addressing modes. Different computer architectures vary greatly as to the number of addressing modes they provide in hardware. There are some benefits to eliminating complex addressing modes and using only one or a few simpler addressing modes, even though it requires a few extra instructions, and perhaps an extra register. It has proven much easier to design pipeline CPUs if the only addressing modes available are simple ones. Most RISC machines have only about 5 simple addressing modes, while CISC machines such as the DEC VAX SuperMINI have over a dozen addressing modes, some of which are quite complicated. The IBM System/360 mainframe had only 3 addressing modes. A few more have been added for the System/390. When there are only a few addressing modes, the particular addressing mode required is usually encoded within the instruction code. But when there are lots of addressing modes, a specific field is often set aside in the instruction to specify the addressing mode. The DEC VAX allowed multiple memory operands for almost all instructions, and so reserved the first few bits of each operand specifier to indicate the addressing mode for that particular operand. Keeping the addressing mode specifier bit separate from the opcode operation bits produces an orthogonal instruction set. Even on a computer with many addressing modes, measurements of actual programs indicate that the simple addressing modes listed below account for some 90% or more of all addressing modes used. Since most such measurements are based on code generated from high-level languages by compilers, this reflects to some extent the limitations of the compilers being used. Useful side effect: some instruction set architectures, such as Intel x86 and IBM/360 and its successors, have a load effective address instruction. This performs a calculation of the effective operand address, but instead of acting on that memory location, it loads the address that would have been accessed into a register. This can be useful when passing the address of an array element to a subroutine. It may also be a slightly sneaky way of doing more calculations than normal in one instruction. For example, using such an instruction with the addressing mode base plus index plus offset allows one to add two registers and a constant together in one instruction. Simple addressing modes for code. Equals absolute or direct equals. Plus plus plus, jump address, plus plus plus. The effective address for an absolute instruction addresses the address parameter itself with no modifications. Equals PC relative equals. Plus plus plus, jump offset jump relative, plus plus plus. The effective address for a PC relative instruction addresses the offset parameter added to the address of the next instruction. This offset is usually signed to allow reference to code both before and after the instruction. This is particularly useful in connection with jumps, because typical jumps are to nearby instructions. Measurements of actual programs suggest that an 8 or 10-bit offset is large enough for some 90% of conditional jumps. Another advantage of PC relative addressing is that the code may be position independent, that is, it can be loaded anywhere in memory without the need to adjust any addresses. Some versions of this addressing mode may be conditional, referring to two registers, one register or no registers, implicitly referring to some previously set bit in the status register. See also conditional execution below. Equals register indirect equals. Plus plus plus, jump via reg, plus plus plus. The effective address for a register indirect instruction is the address in the specified register. For example, to access the content of address register A7. The effect is to transfer control to the instruction whose address is in the specified register. Many RISC machines, as well as the CISC IBM System/360 and successors, have subroutine call instructions that place the return address in an address register. The register indirect addressing mode is used to return from that subroutine call. Sequential addressing modes. Equals sequential execution equals. Plus plus, NOP execute the following instruction, plus plus. The CPU, after executing a sequential instruction, immediately executes the following instruction. Sequential execution is not considered to be an addressing mode on some computers. Most instructions on most CPU architectures are sequential instructions. Because most instructions are sequential instructions, CPU designers often add features that deliberately sacrifice performance on the other instructions branch instructions in order to make these sequential instructions run faster. Conditional branches load the PC with one of two possible results, depending on the condition. Most CPU architectures use some other addressing mode for the taken branch, and sequential execution for the not taken branch. Many features in modern CPUs, instruction prefetch and more complex pipelining, out-of-order execution, etc., maintain the illusion that each instruction finishes before the next one begins, giving the same final results, even though that's not exactly what happens internally. Each basic block of such sequential instructions exhibits both temporal and spatial locality of reference. CPUs that do not use sequential execution with a program counter are extremely rare. In some CPUs, each instruction always specifies the address of next instruction. Such CPUs have an instruction pointer that holds that specified address. It is not a program counter because there is no provision for incrementing it. Such CPUs include some drum memory computers, the SECD machine, and the RTX 32P. Other computing architectures go much further, attempting to bypass the von Neumann bottleneck using a variety of alternatives to the program counter. Conditional execution equals. Some computer architectures have conditional instructions or conditional load instructions which can in some cases obviate the need for conditional branches and avoid flushing the instruction pipeline. An instruction such as a compare is used to set a condition code, and subsequent instructions include a test on that condition code to see whether they are obeyed or ignored. Skip equals. Plus 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 plus, skip reg1 reg2 skip the following instruction if reg1 equals reg2, plus 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 plus. Skip addressing may be considered a special kind of PC relative addressing mode with a fixed +1 offset. Like PC relative addressing, some CPUs have versions of this addressing mode that only refer to one register or no registers, implicitly referring to some previously set bit in the status register. Other CPUs have a version that selects a specific bit in a specific byte to test. Unlike all other conditional branches, a skip instruction never needs to flush the instruction pipeline, though it may need to cause the next instruction to be ignored. Simple addressing modes for data. Equals register equals. Plus 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 plus, mul reg1 reg2 reg3 reg1, equals reg2 reg3. Plus 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 plus. This addressing mode does not have an effective address and is not considered to be an addressing mode on some computers. In this example, all the operands are in registers, and the result is placed in a register. Equals base plus offset, and variations equals, this is sometimes referred to as base plus displacement. Plus 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 plus, load reg base offset reg, equals RAM, base plus offset, plus 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 plus. The offset is usually assigned 16-bit value. If the offset is 0, this becomes an example of register indirect addressing. The effective address is just the value in the base register. On many RISC machines, register 0 is fixed at the value 0. If register 0 is used as the base register, this becomes an example of absolute addressing. However, only a small portion of memory can be accessed. The 16-bit offset may seem very small in relation to the size of current computer memories. It could be worse. IBM System/360 mainframes only have an unsigned 12-bit offset. However, the principle of locality of reference applies. Over a short time span, most of the data items a program wants to access are fairly close to each other. This addressing mode is closely related to the indexed absolute addressing mode. Example 1, within a subroutine a programmer will mainly be interested in the parameters in the local variables, which will rarely exceed 64 kilobytes, for which one base register suffices. If this routine is a class method in an object-oriented language, then a second base register is needed which points at the attributes for the current object. Example 2, if the base register contains the address of a composite type, the offset can be used to select a field from that record. Equals immediate literal equals. Plus 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 plus, add reg1 reg2 constant reg1, equals reg2 plus constant. Plus 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 plus. This addressing mode does not have an effective address, and is not considered to be an addressing mode on some computers. The constant might be signed or unsigned. For example, move $$fiadaba, DO to move the immediate hex value of fiadaba into register DO. Instead of using an operand from memory, the value of the operand is held within the instruction itself. On the DEC VAX machine, the literal operand sizes could be 6, 8, 16, or 32 bits long. Andrew Tannenbaum showed that 98% of all the constants in a program would fit in 13 bits. Equals implicit equals. Plus plus, clear carry bit, plus plus. Plus plus, clear accumulator, plus plus. The implied addressing mode, also called the implicit addressing mode, does not explicitly specify an effective address for either the source or the destination. Either the source or destination effective address is implied by the opcode. Implied addressing was quite common on older computers. Such computers typically had only a single register in which arithmetic could be performed, the accumulator. Such accumulator machines implicitly reference that accumulator in almost every instruction. For example, the operation can be done using the sequence, the destination is implied in every load, and add instruction. The source is implied in every store instruction. Later computers generally had more than one general-purpose register or RAM location which could be the source or destination or both for arithmetic, and so later computers need some other addressing mode to specify the source and destination of arithmetic. Among the x86 instructions, some use implicit registers for one of the operands or results. Many computers have one special-purpose register called the stack pointer, which is implicitly incremented or decremented when pushing or popping data from the stack, and the source or destination effective address is the address stored in that stack pointer. Many 32-bit computers have more than one register which could be used as a stack pointer and so use the register auto-increment in direct addressing mode to specify which of those registers should be used when pushing or popping data from a stack. Some current computer architectures contain some instructions with implicit operands in order to maintain backwards compatibility with earlier designs. On many computers, instructions that flip the user system mode bit, the interrupt enable bit, etc. implicitly specify the special register that holds those bits. This simplifies the hardware necessary to trap those instructions in order to meet the Pope and Goldberg virtualization requirements. On such a system, the trap logic does not need to look at any operand, but only at the opcode. A few CPUs have been designed where every operand is always implicitly specified in every instruction, zero-operand CPUs. Other addressing modes for code or data. Absolute direct equals. Load reg address, This requires space in an instruction for quite a large address. It is often available on CISC machines which have variable length instructions, such as x86. Some RISC machines have a special load upper literal instruction which places a 16-bit constant in the top half of a register. An OR literal instruction can be used to insert a 16-bit constant in the lower half of that register, so that a full 32-bit address can then be used via the register in direct addressing mode, which itself is provided as base plus offset with an offset of 0. Indexed absolute equals. Load reg index address, This also requires space in an instruction for quite a large address. The address could be the start of an array or vector, and the index could select the particular array element required. The processor may scale the index register to allow for the size of each array element. Note that this is more or less the same as base plus offset addressing mode, except that the offset in this case is large enough to address any memory location. Example 1, within a subroutine, a programmer may define a string as a local constant or a static variable. The address of the string is stored in the literal address in the instruction. The offs to euro, which character of the string to use on this iteration of a loop is stored in the index register. Example 2, a programmer may define several large arrays as globals or as class variables. The start of the array is stored in the literal address of the instruction that references it. The offs to euro, which item from the array to use on this iteration of a loop is stored in the index register. Often the instructions in a loop reuse the same register for the loop counter and the offsets of several arrays. Base plus index equals. Load reg base index, The base register could contain the start address of an array or vector, and the index could select the particular array element required. The processor may scale the index register to allow for the size of each array element. This could be used for accessing elements of an array passed as a parameter. Base plus index plus offset equals. Load reg base index offset, The base register could contain the start address of an array or vector of records, the index could select the particular record required, and the offset could select a field within that record. The processor may scale the index register to allow for the size of each array element. Scaled equals. Load reg base index, The base register could contain the start address of an array or vector data structure, and the index could contain the offset of the one particular array element required. This addressing mode dynamically scales the value in the index register to allow for the size of each array element. For example, if the array elements are double precision floating point numbers occupying 8 bytes each, then the value in the index register is multiplied by 8 before being used in the effective address calculation. The scale factor is normally restricted to being a power of 2, so that shifting rather than multiplication can be used. equals register indirect equals plus 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 load reg1 base plus 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 plus. A few computers have this as a distinct addressing mode. Many computers just use base plus offset with an offset value of 0. For example, equals register auto increment indirect equals plus 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 load reg base plus 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 plus. After determining the effective address, the value in the base register is incremented by the size of the data item that is to be accessed. For example, plus would access the content of the address register A7, then increase the address pointer of A7 by 1. Within a loop, this addressing mode can be used to step through all the elements of an array or vector. In high-level languages it is often thought to be a good idea that functions which return a result should not have side effects. This addressing mode has a side effect in that the base register is altered. If the subsequent memory access causes an error leading to an interrupt, then restarting the instruction becomes much more problematic since one or more registers may need to be set back to the state they were in before the instruction originally started. There have been at least 2 computer architectures which have had implementation problems with regard to recovery from interrupts when this addressing mode is used. Motorola 68000 could have 1 or 2 auto-increment register operands. The 68010 Plus resolved the problem by saving the processor's internal state on bus or address errors. DEC VAX could have up to 6 auto-increment register operands. Each operand access could cause 2 page faults. Of course, the instruction itself could be over 50 bytes long and might straddle a page boundary as well. Equals auto-decrement register indirect equals plus 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 load reg base plus 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 plus. Before determining the effective address, the value in the base register is decremented by the size of the data item which is to be accessed. Within a loop, this addressing mode can be used to step backwards through all the elements of an array or vector. A stack can be implemented by using this mode in conjunction with the previous addressing mode. See the discussion of side effects under the auto-increment addressing mode. Equals memory indirect equals, any of the addressing modes mentioned in this article could have an extra bit to indicate indirect addressing, that is the address calculated using some mode is in fact the address of a location which contains the actual effective address. Indirect addressing may be used for code or data. It can make implementation of pointers or references or handles much easier, and can also make it easier to call subroutines which are not otherwise addressable. Indirect addressing does carry a performance penalty due to the extra memory access involved. Some early mini-computers had only a few registers and only a limited addressing range. Hence the use of memory indirect addressing was almost the only way of referring to any significant amount of memory. Equals PC relative equals plus 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 load reg1 base equals PC offset reg1 equals RAM PC plus offset plus 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 plus. The PC relative addressing mode is used to load a register from a constant stored in program memory a short distance away from the current instruction. It can be seen as a special case of the base plus offset addressing mode, one that selects the program counter as the base register. There are a few CPUs that support PC relative data references. Such CPUs include the x86-64 architecture and the 64-bit ARMv8A architecture have PC relative addressing modes, called IP relative in x86-64 and literal in ARMv8A. The Motorola 6809, a very advanced 8-bit CPU designed in 1978, also supports a PC relative addressing mode. The PDP-11 architecture, the VAX architecture, and the 32-bit ARM architectures support PC relative addressing by having the PC in the register file. When this addressing mode is used, the compiler typically places the constants in a literal pool immediately before or immediately after the subroutine that uses them, to prevent accidentally executing those constants as instructions. This addressing mode, which always fetches data from memory or stores data to memory and then sequentially falls through to execute the next instruction, should not be confused with PC relative branch, which does not fetch data from or store data to memory, but instead branches to some other instruction at the given offset. Obsolete addressing modes. The addressing modes listed here were used in the 1950–1980 period, but are no longer available on most current computers. This list is by no means complete. There have been many other interesting and peculiar addressing modes used from time to time, for example absolute minus logical OR of 2 or 3 index registers. Equals multi-level memory indirect equals, if the word size is larger than the address, then the word referenced for memory indirect addressing could itself have an indirect flag set to indicate another memory indirect cycle. This flag is referred to as an indirection bit, and the resulting pointer is a tagged pointer, the indirection bit tagging whether it is a direct pointer or an indirect pointer. Care is needed to ensure that a chain of indirect addresses does not refer to itself. If it does, one can get an infinite loop while trying to resolve an address. The IBM 1620, the Data General Nova, the HP 2100 series, and the NAR2 each have such a multi-level memory indirect, and could enter such an infinite address calculation loop. The memory indirect addressing mode on the Nova influenced the invention of indirect threaded code. The DECP-DP10 computer with 18-bit addresses and 36-bit words allowed multi-level indirect addressing with the possibility of using an index register at each stage as well. Memory mapped registers on some computers, the registers were regarded as occupying the first 8 or 16 words of memory. This meant that there was no need for a separate add register to register instruction. One could just use the add memory to register instruction. In the case of early models of the PDP-10, which did not have any cache memory, a tight inner loop loaded into the first few words of memory ran much faster than it would have in magnetic core memory. Later models of the DECP-DP11 series mapped the registers onto addresses in the input-output area, but this was primarily intended to allow remote diagnostics. Confusingly, the 16-bit registers were mapped onto consecutive 8-bit byte addresses. Memory indirect and auto increment equals, the DECP-DP8 minicomputer had 8 special locations. When accessed via memory indirect addressing, these locations would automatically increment after use. This made it easy to step through memory in a loop without needing to use any registers to handle the steps. The Data General Nova minicomputer had 16 special memory locations at addresses 16 through 31. When accessed via memory indirect addressing, 16 through 23 would automatically increment before use, and 24 through 31 would automatically decrement before use. 0 page equals, the Data General Nova, Motorola 6800 family, and MOS Technology 6502 family of processors were families of processors with very few internal registers. Arithmetic and logical instructions were mostly performed against values in memory as opposed to internal registers. As a result, many instructions required a 2-byte location to memory. Given that opcodes on these processors were only 1 byte in length, memory addresses could make up a significant part of code size. Designers of these processors included a partial remedy known as zero-page addressing. The initial 256 bytes of memory could be accessed using a 1-byte absolute or indexed memory address. This reduced instruction execution time by 1 clock cycle and instruction length by 1 byte. By storing often used data in this region, programs could be made smaller and faster. As a result, the zero page was used similarly to a register file. On many systems, however, this resulted in high utilization of the zero-page memory area by the operating system and user programs, which limited its use since free space was limited. Direct page equals, the zero-page address mode was enhanced in several late-model 8-bit processors, including the WDC 65816, the CSG 65CE02, and the Motorola 6809. The new mode, known as direct page addressing, added the ability to move the 256-byte zero-page memory window from the start of memory to a new location within the first 64 kilobytes of memory. The CSG65CE02 allowed the direct page to be moved to any 256-byte boundary within the first 64 kilobytes of memory by storing an 8-bit offset value in the new base page register. The Motorola 6809 could do the same with its direct page register. The WDC 65816 went a step further and allowed the direct page to be moved to any location within the first 64 kilobytes of memory by storing a 16-bit offset value in the new direct register. As a result, a greater number of programs were able to utilize the enhanced direct page addressing mode versus legacy processors that only included the zero-page addressing mode. Scaled index with bounds checking equals. This is similar to scaled index addressing, except that the instruction has two extra operands, and the hardware checks that the index value is between these bounds. Another variation uses vector descriptors to hold the bounds. This makes it easy to implement dynamically allocated arrays and still have full bounds checking. Register indirect byte within word equals. The DECP DP10 computer used 36-bit words. It had special instructions which allowed memory to be treated as a sequence of bytes. A one-word sequence descriptor in memory, called a byte pointer, held the current word address within the sequence, a bit position within a word, and the size of each byte. Instructions existed to load and store bytes via this descriptor, and to increment the descriptor to point at the next byte. Much DEC software used 5 7-bit bytes per word, with 1 bit per word unused. Implementations of C had to use 4 9-bit bytes per word, since the malloc function in C assumes that the size of an int is some multiple of the size of a char. The actual multiple is determined by the system-dependent compile-time operator sysiov. Index next instruction equals, the Elliott 503, the Elliott 803, and the Apollo guidance computer only used absolute addressing, and did not have any index registers. Thus, indirect jumps, or jumps through registers, were not supported in the instruction set. Instead, it could be instructed to add the contents of the current memory word to the next instruction. Adding a small value to the next instruction to be executed could, for example, change a jump 0 into a jump 20, thus creating the effect of an index jump. Note that the instruction is modified on the fly and remains unchanged in memory, that is, it is not self-modifying code. If the value being added to the next instruction was large enough, it could modify the opcode of that instruction as well as or instead of the address. External links, addressing modes in assembly language, addressing modes. References